Hi, I'm Guang, I'm 15 years old. In this lesson of theoretical mechanics on the mechanical waves and mechanical vibrations, we are taking a look at pendulums, right? So, in the last lesson, what we had was about springs, where the main focus was the Hooke's law, where you have F is equal to negative kx. But this time, we're taking a look into pendulums. Right, so first of all, the few things about pendulums that you have to know. Now for here, let's just say our pendulum hangs from a ceiling, alright? So let's just say this is our ceiling. So a pendulum hangs from here. Let's say we have a pendulum like this. Now what would you do with this kind of bob hanging from a string, hanging from a ceiling? Now of course, you would want to shift it a bit from its original position and see what it does, right? So let's shift it a bit from its original position. And let's say it goes here. So what would be the direction of its movement? Well, that will probably be in an arc, alright? So let's just say you move it in this direction. But of course, if you want to see how this angle goes, you can always use your right hand rule. You grip it in the direction of its movement and angular movement is outwards, alright? So beware, it's always the right hand rule when you want to find its movement. Alright, so going outwards, but that's just some extra information you want to know. But alright, so let's just say you moved it upwards. So what's so special about that? Now, let's draw a free body diagram of this bob. So, this bob here that we're going to have, let's say it will be from this position where you have the slanted string. So, the force exerted by the string, wait, this needs to go into its mass center since it's a free body diagram, alright? So let's say this is its mass center. So the force exerted by the string would be the tension, alright? So this is the tension force. And what other forces are there? Well, of course, there will be the weight. You can write W here or you can just write mg, alright? It depends on how you like to write it. So these are the two forces acting on the bob, where you have weight and you have tension. But of course here we are just doing it on, let's say, planet Earth or something. It depends, let's say if you're doing it outer space, then maybe you won't have weight and just goes in circles, but well, those will be different cases. So you do have a weight and a tension. Now, what are you going to do with these two? Now, when you think about how the bob moves, it is within your arc, or at most a semicircle, right? So, how exactly do you think you can separate these two into its components? Which do you have to separate into its components? Which do you not have to? Alright. So if you have thought about it, here, when you have this string pulling it with a tension force, and it is moving in an arc, in a circular motion, well, maybe not exactly a full circle, but you get a point, similar to whatever you would have learned in circular motion. So one of them you might know it as centripetal, while the other is tangential. Now, what's so special about these two again? So, centripetal would be your T, your centripetal force. So, centripetal force is T, and what is a tangential force? Well, that is where we have to separate your weight into its two components. So, separating weight into its two components, well, how are you going to separate it? Maybe you can have one perpendicular whatever, but no, you wouldn't. Since here you have a T, you would want a component that pretty much cancels out with your t. Alright, so a component here, let's say we call it f1. And of course, when you have this component, you have another component that is perpendicular to your component. And with this perpendicular component, that would be the second component for your weight. Alright, and let's call it f2. Alright, so we have separated weight into two separate components, f1 and f2. f1 is along the same line as tension, but in the opposite direction as the tension force, or f2 is perpendicular to both of them. So f2 will be your tangential force. And when you see it as the movement in the bob, that will just be along your arc. Alright, so now that we know these, can we think about how else can we express f1 and f2? But of course, you might want to know how much exactly do you separate the bob from its original position. Well, we can label the angle above as theta, alright? So you have a theta angle, and you move the bob theta angles away from its original position. And that means your theta here can actually be transferred into this part. Alright, so when you have this, is it much simpler to find f1 and f2? So f1 and f2. Now, f1, what you will be seeing is mg cosine theta, or it would just be t. Alright, so that is f1. Now, we take a look at f2. So, f2, what you will realize is, maybe you just think it is just mg sine theta, right? But, well, there's a little problem over here, and that is if you have learned about restoring forces. Since if you realize, when you move a pendulum, you move it outwards a little bit, it will always go back. And at last, it could just go back to its original position. And that is what's so special about restoring force. But now, why do we need to know that over here? Well, you see, now if you move your bob out a positive angle theta, of course, this f2 would want to move it back into its original position. But do you realize that, let's say, when you move it outwards, it's positive, that means when you move it backwards, it's negative, which means f2 is countering your original motion, where that means it is a negative, right? So you have to be aware that this in front here actually has a negative. Alright, so that is what's so special about restoring forces in this case. So restoring forces, just have to be aware, it has to go back to its original position, right? So f2 is negative mg sine theta. Is there any other ways, well, we could change it? Well, yes, there is. Now, that involves Newton's second law. Well, you have F is equal to ma, but how are we going to use that here? Let's just take a look at how we're going to apply it first. F is equal to ma. A in this case is not the normal acceleration you would think of, since A in this case is more of an angular acceleration, or some of you might represent it as something like beta or whatever, alright? You just have to define it clearly. Right, so F is equal to ma. Well, now we don't really have the negative, since A itself can be a positive or a negative, alright? So F is equal to ma. How can we change this A? If you have learned a bit of differentiation integration, then you might know that A can be changed into the first derivative of v with respect to time. V either being speed or velocity, well, we mainly prefer speed in this case. So in this case, that will be your angular speed. So here you have m multiplied by the first derivative of angular speed with respect to time. How about we change that into a second derivative? So a second derivative of this distance with respect to time. But then again, what's so special about this distance, or more specifically, your arc length, right? So this arc length over here, is there any way you can find it? But of course, in this case, since we're just looking at simple singular pendulums, not double, not triple, just singular, and just a simple one, since your little string is ideal. And what does that mean by an ideal scenario? You do not have the string expanding, contracting, or just going out of shape and all, right? So its length is fixed, and let's say we call that L. So if you have learned a little bit of calculus, theta is in radians, you're given the radius length of L. Can you find its arc length? Well, yes you can. That will just be your angle multiplied by your radius. Well, in this case, it'll become m multiplied by the second derivative of theta times L. And this is, of course, with respect to t. So what did I say just now about L? L is fixed. So you take a look at this. You're differentiating something with respect to time. And since L is fixed, that doesn't really matter inside, right? So you can take the L out and you'll get m multiplied by L multiplied by your angular acceleration. Alright? So what would be so special in this case here? Now you have m multiplied by L multiplied by angular acceleration. So if you have thought about this, now angular acceleration, you will have to realize that actually originally you might think about, since this is moving in your circular motion direction, so actually originally here what I said just now was not exactly right, since if you realize, if this is angular acceleration, how do you get an actual L? So actually in the beginning here, this A is actually a linear acceleration, which is how at last you have an extra L multiplied by angular acceleration, right? So sorry about that. Now, angular acceleration, what is so special about this part? And what can we do with it? How about we take a look at some things that are not exactly derived from each other. And what do I exactly mean by that? So you realize originally you have a negative mg sine theta, and afterwards you have this ml second derivative of theta with respect to t. Now how about we equate these two together? Well, you might think, yeah, they're already equal, but we will bring them out to take a look at them separately. Right, so here is actually where we have already formed a differential equation. Now, using this differential equation, we can move all of them to the same side. And of course, since both of them have m, you can just simplify them out. Right, so you're going to have L second derivative of theta, or with respect to t, or just angular acceleration. Then you're going to add g sine theta, and this is equal to 0. Right, and now we're going to see your angular acceleration add on to g over L sine theta is equal to 0. Now at this stage, you might not be able to solve it. You might not know how to solve it. Now, is there any other way we can get out of this? So, one way to fix this problem is, with your angular acceleration, you leave it as the same. G over L, you leave it as the same. Sine theta is where you change it. Sine theta, how are you going to change this? Well, if you have learned Maclaurin series, then you will just change that into theta minus 1 over 3 factorial theta cubed plus 1 over 5 factorial theta to the power of 5, and so on. Right? So, in this case, if our theta is very, very small, or even approaches to 0, you realize the terms other than theta is pretty much negligible. Well, then or you can just write when theta approaches to 0 something, or even you might see in some books where they just write by small angle approximation. So in that case, you can just make this a theta, alright? So that is when theta approaches to 0. So when you're conducting the experiment for your pendulum, you would preferably want a longer string so that when you move it to the angle of very small, it is more detectable and all, alright? So then we take a look at this again. Is there something more familiar about it, maybe? Or how about we just make a substitution? Make a substitution, not when. So let g over L be equals to omega squared. And you just see your angular acceleration add on to omega squared theta is equal to 0. Now this makes theta seem more solvable, isn't it? Since you have a second derivative and you have a omega squared. So this means your theta could be a sine or a cosine. But whether you want to use sine or cosine, it also depends on what kind of question you have, and of course, when it is better, alright? Now, that means, how about let's just use sine first, alright? So, when you have sine, since you have omega squared, that means you have omega t, right? Since if you differentiate it twice, you just have 2 omegas coming out. Now, for this, when you have a certain amplitude multiplied to it, it doesn't really matter, since both of them would still have the same amplitude. And of course, if you add on another initial phase, that also doesn't matter, since it is just a constant within your sine. So this could be a possible form of your final solution, but whether it's sine or cosine, it will still again be up to you. Right? What's so special about all these? What have we done all these for? So we take a look at this again. Theta is equal to a sine omega t plus phi. Now, what is one of the most common pendulum formulas you will see? Formulas about pendulum that you'll see. Of course, you might see the period of a pendulum. Now, period of a pendulum, it is more often than not represented by capital T. Now, this capital T, how are we going to find it? Since you already have this formula for theta, you can actually find your period. Since you do have the sine function, and the period of a sine function would just be 2 pi divided by whatever is in front of the variable, which in this case you have omega. So whatever is in front of these variable, you might refer to them as different things in different conditions, right? Like maybe sometimes it's period and all, but other times it could be a frequency, which I'll explain more later. So now with this omega, you can put in the original omega, which is square root g over L, to get 2 pi square root L over g, reciprocal since it's in the denominator. Right, so this will be the very familiar formula that you see. Your period is equal to 2 pi multiplied by square root L over g. Now, what was I talking about just now? There was a frequency. Yes, a frequency. 1 over t, isn't it? Well, isn't it just as simple as that? Well, yes, you can have it as simple as this. But you would also have to be aware. Maybe there's another form of representing this. Maybe you would realize that 2 pi f is equal to omega. Well, in this case, do you realize anything special? If you just multiply 2 pi to the other side, yeah, this is just omega. But what's going on here? So you do have your frequency, but since if you multiply it by 2 pi, a normal frequency will just become your angular frequency. So an angular frequency, or appear in this case, it all depends on what kind of equation you're looking at, since the same thing could represent different meanings with the same value in different cases. Right, so these two are the main formulas that you will be seeing quite a lot, especially when you're dealing with pendulum. Right, so that is pretty much all we have in this lesson. So let's just quickly run through what we had from the start. Now from the start, we took a look at a simple pendulum setup. And with this pendulum setup, you move it to the right by a little bit, make a free body diagram of it, and see what kind of vectors you can get, what kind of forces you can get. And by analysis of these forces, especially F2, where you have two different ways of representing it, whether it's from a free body diagram or just F is equal to ma. And with that, you can set up a differential equation. And then you solve these differential equations and get a final answer for your theta. And with that theta, you further analyze it in order to get the period and its frequency. Alright, so that's pretty much it for this lesson. I hope that you can understand so far. I'll be ending it here, and thank you for your watching.